Alright, so throughout the first couple of videos, I've made reference to opposite charges attracting, like charges repelling. And while this is something that may be intuitive or common knowledge, you may have heard these types of things before, what we really want to do now is take a minute to study them in depth and talk about the details of like charges repelling and opposite charges attracting. And those details are really going to come from a discussion of the electrostatic force, one of the fundamental forces in nature. So the electrostatic force is described by Coulomb's law, which is that the force is equal to K Q1 Q2 over R squared. K is a constant, Q's are the charges, and R is the separation. So K is the Coulomb constant, to be specific. Its amount is 9 times 10 to the ninth. Units are Newton meters squared per Coulomb squared. It is set up to give us newtons that cancel with the coulombs from the charges and the meters squared from the R squared. Those Q's, Q1 and Q2, that is amount of charge. So you have two amounts of charge. They either push or pull on each other depending on if they're opposite charges or like charges. And the amount of the force also depends on the separation of the charges. So if we look at this equation, you have bigger charges, of course you're going to have a bigger force. You have a small separation. When they're really close together, you have a stronger force. If they're really far apart, we divide by that R squared, the force isn't as strong. So we can see too, if we were plugging in values of Q1 and Q2, if one is positive and one is negative, we would call those opposite charges. A positive times a negative, Q1 times Q2. Positive times a negative is negative, which means the charges will attract. The negative means that separation is going to decrease. They're going to get closer together because they are being pulled together, and that is what the negative represents in this equation. Similarly, if we had two positive charges, a positive times a positive is positive, or if we had two negative charges, a negative times a negative is also positive. So if the force is positive, the charges are repelling. They're pushing each other away because they're either both positive or both negative. Furthermore, we can see that the dependence on Q1 and Q2 is what we call linear. If you increase Q, say double it, have twice as much charge on one of those charges, you get twice as much force. However, the R is squared. It's an inverse square law. Because it's squared, the effect is stronger. So, if you were to double the separation, make these things twice as far apart, you would get 4 times less force, 4 being the square of 2. Similarly, if you have the separation, if you were to bring them closer together, you get more force, and 4 times more force. You divide it by 2, and then you square that 2 to get the effect of 4 times as much. And the same thing would go for, say, we were to triple the separation, we would get 9 times less force. If we were to divide the separation by 3, we would get 9 times more force. All right. Now, how do we actually measure charge? How is charge measured? Turns out the units are coulombs. You can probably guess who did a lot of the studying of this stuff. A guy named Coulomb. He has his name all over everything when it comes to electricity. So charge is measured in coulombs, and it turns out coulombs are a pretty big unit, which means there's only a tiny, tiny amount on any given electron or proton. Turns out each electron has Q sub e for the charge on an electron. The charge is negative, because it's an electron, 1.6 times 10 to the minus 19 coulombs. It's a very, very small amount of charge. Protons have the exact same amount of charge, only positive, and that's why if you have an equal amount of protons and electrons, you have a neutral charge, because the amounts come in the same size. The only difference is that electrons are negative, protons are positive. So with this newfound force, let's compare it to another old familiar face, that of the gravitational force. And if you look at these, we can see that their equations are very similar. We have the universal law of gravitation, G m1 m2 over r squared, and the electrostatic force, K q1 q2 over r squared. Both are a constant, 2 of something, and then divided by the separation squared. And we're going to see this again in magnetism. It turns out the fundamental forces all have this 1 over r squared dependence, what they call the inverse square law dependence. But let's look now at the relative amount of these. Let's work through just a quick example comparing the electrostatic and gravitational forces. So let's take 2 protons and separate them by 1 meter, and we are going to compare the electrostatic and gravitational forces between those 2 protons. So we just looked at their equations. They're very similar. They both have a constant, K and G, 9 times 10 to the 9th Newton meter squared per Coulomb squared, 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. The only difference in the units are those coulombs or kilograms, whether we're talking about charges or masses. Well, gathering up our other useful quantities, the charge on each proton is going to be 1.6 times 10 to the minus 19 coulombs. The mass of each proton is very, very small, 1.67 times 10 to the minus 27 kilograms. And of course, they're both separated by 1 meter. So if we go to plug all of this in, there's our electrostatic force, K, Q1, Q2 over R squared. Coulombs times coulombs cancels with coulombs squared. We have meters squared up top, meters squared on the bottom. We're going to end up with a force in newtons. And the electrostatic force is 2.3 times 10 to the minus 28 newtons. Seems pretty small, right? 10 to the minus 28, that is pretty small, I'll agree. But now let's look at the gravitational force. If we plug numbers into the gravitational force, we have our gravitational constant, 6.67 times 10 to the minus 11, Newton meters squared per kilogram squared. We have the mass of 1 proton times the mass of another proton, 1.67 times 10 to the minus 27 kilograms, and again, and then all over that 1 meter squared. And the unit analysis works similarly. We have kilograms times kilograms, which would be kilograms squared, cancels with the kilograms squared on the bottom. Then we have meters squared up top, canceling with meters squared on the bottom. We again are left with units of newtons. A force makes sense. But look at that. Whoa, that is tiny. 1.86 times 10 to the minus 64 newtons. There is barely any gravitational force between two protons. I mean, the electrostatic force is small too, but if we compare their relative size, if we were to divide the electrostatic force by the gravitational force, we can see that the electrostatic force is 1.24 times 10 to the 36 times greater than the gravitational force. That is, like, I cannot underscore this enough, enormous. That is huge. The electrostatic force is a lot stronger than the gravitational force, it turns out. Turns out gravity is actually a pretty weak force. I mean, we think of it as strong, it keeps us stuck to the planet, but in the grand scheme of things, it isn't really a very strong force. So that's going to conclude our video on the electrostatic force. We will have one last video on electric fields, and we will be done with the Chapter 10 material.